Hi everyone. I gave you that Google survey yesterday, and based on the survey, I see that there's still a little bit of confusion with 5' and 3', leading and lagging strands, the orders of DNA replication, and functions of DNA polymerase 1, DNA polymerase 3, and then some of the other enzymes. So what we're going to do today is I'm just going to review basically a summary of everything we've learned about DNA replication. And somebody gave me a great suggestion of diagramming step by step, even though in reality there's like multiple enzymes, multiple types of these enzymes working kind of at the same time, but we'll break it up step by step, and then you're going to diagram it step by step rather than diagramming it all together. So I'm first going to start off with just reviewing 5' to 3'. If you did not see the YouTube video that I put up reviewing the DNA structure homework that you did, and you're still struggling with 5' and 3', you might want to watch that video because I do explain it there. But just quickly, how to tell the 5' and 3' strand apart. So I drew out the strands, right? First of all, let's just quick review. DNA is made up of multiple nucleotides. So what's a nucleotide? This is a nucleotide. A phosphate group, a 5-carbon sugar, and a nitrogenous base. That nitrogenous base would be your adenine, thymine, cytosine, guanine. Here's one nucleotide, right? And here's another nucleotide. What's going to bond these sugar and phosphates from one nucleotide to the other together to create the backbone of DNA? A phosphodiester bond, a covalent bond. So this making up the 2 strands of DNA. Now DNA strands are anti-parallel, meaning one side's going to go from 5' to 3', and another side's going to go from 3' to 5'. How do we figure that out? Well, the first thing that you want to do is you want to look at the first carbon sugar in each strand. So here's one sugar, here's another. Notice how they run anti-parallel. In one sugar, the oxygen is facing up, and the other one, the oxygen is facing down. You need to count the carbons. Oxygen, if we look at this strand starting at the top, you count clockwise. 1', 2', 3', 4', 5'. What's going to determine the strand, what the start of this strand is? Well, it's going to be the carbon that's hanging off the strand. This 5' carbon is facing the outside of the strand. This 3' carbon is facing the inside of the strand. This is the 5' side of DNA. If we look at this side, 1', 2', 3', 4', 5', the 3' strand is hanging off of the DNA, so this would be the 3' side. And they run anti-parallel, so once you figure that out, you know that this is the side that goes from 5' to 3'. This is the side that goes from 3' to 5'. Make sure that you take some time to review, and that's what we're doing today. You need to take your time and review. Go back to the YouTube videos, go back to the Ed Puzzle, look at the questions that you answered in the Ed Puzzle, look at the answers that I'm posting. Okay, really take your time reviewing this material, making sure that you're using all of the resources that I'm posting for you, because I am giving you a lot, but they're all there to help you. I drew a really bad piece of DNA, but showing the 2 different strands, 2 different colors. You got a blue backbone strand, you got a green one, and we have some different bases, adenine, thymine, cytosine, guanine, because it's DNA, and I color-coded them, so I matched them up. Let's get started with the DNA replication process. So step 1 the first thing that needs to happen is what? We are trying to replicate DNA. DNA replication is semi-conservative. So we need to use each of these strands as a template. How are we going to do that? By unzipping the DNA. What enzyme unzips the DNA? Well, that's going to be helicase. So the first thing that happens is helicase unzips DNA. So in between these bases, there are hydrogen bonds. Hydrogen bonds are weak. So that allows helicase to, it's an enzyme, helicase to come through and break through the hydrogen bonds to separate the strands of DNA. And it's not going to unzip through all of it all at once, right? It's going to move through and slowly unzip the DNA, slowly moving from the top of the DNA and then going to break through all those bonds eventually, separating the two strands. So this enzyme helicase is coming through, breaking the hydrogen bonds between DNA and unzipping it. Now, as this is happening, right, because it's only happening, it's happening from top to bottom, and then you have these bottom strands that are still intertwined. We need an enzyme that's going to, in this case, prevent supercoiling of the DNA. Basically, you don't want the DNA to become wounded at this bottom part. You don't want the rest of the DNA, as helicase is coming through and unzipping it, you don't want the rest of the strands to become intertwined and overwound together, because we're trying to separate them to replicate DNA. So that's the purpose of having an enzyme called gyrase, which is a topoisomerase. So gyrase, making sure that as helicase is unzipping the DNA, that the rest of the strands are not becoming intertwined together. So that would be step 2. Gyrase, making sure that there's no supercoiling of the DNA, that the DNA is not becoming overwound, because we're trying to keep it separate. Okay, so step 1, helicase unzipping it. And step 2, gyrase, preventing the supercoiling of the DNA. Now, the actual replication process needs to get started. We need RNA polymerase, or in other words, primase, that enzyme that's going to lay nucleotides of where DNA polymerase 3 should start. Now, for the purposes of what we're doing, I'm just going to label these strands 3' to 5', 5' to 3'. Okay, so we have these two strands of DNA. DNA polymerase 3 can only create the daughter strand from 5' to 3'. So in order to create the daughter strand 5' to 3', that means that it needs to read the parent strand. In other words, lay the nucleotides from the parent strands 3' to 5' end, because they're anti-parallel. So DNA polymerase needs to make both daughter strands only in the 5' to 3' direction. So RNA polymerase needs to lay down the primers for that. It's going to be laying down RNA nucleotides. I have my chart up here. Try my best to follow it. It's laying down RNA nucleotides on the parent strand's 3' end. I'm just going to do a small chunk. So it can only lay from the parent's 3' end to go in the 5' to 3' direction of the daughter strand. So pink, so laying down an RNA nucleotide. And I'm going to lay down like a couple of RNA nucleotides, because DNA polymerase 3 needs nucleotides to attach onto in order to continue building. Now, it's not going to build DNA polymerase 3 is not going to build on top of these RNA nucleotides, but it needs something to be there in order to continue building. It can't just start building on its own. It needs something to get it started. It needs a couple nucleotides to already be laid down so it can just continue building off of them. RNA polymerase or primase, step 3, laying down RNA primers. So it did it for this strand. We got to look over here. It's got to do it for this strand. So it needs to do it on the 3' to 5' strand. Again, it needs to make them 5' to 3' this direction. This strand would be making it in this direction. Now, primase laid down the RNA nucleotides. DNA polymerase 3 can build off from there in the 5' to 3' direction for the daughter strand. Here, in this strand, the 3' to 5' strand, it's just going to continue building. So the RNA primers are here. That primase laid down. Now DNA polymerase 3 has something to work off of, going from the daughter strand's 5' to 3' direction. And helicase, remembers, unzipping in this direction. So this strand, the daughter strand's moving in the same direction as helicase is unzipping the DNA. This would be called the leading strand because it's going to be one continuous strand because it's following the exact way that helicase is unzipping the DNA. So it's going to be one continuous strand. You only need primase to lay down those RNA nucleotides at the beginning, and now DNA polymerase 3 is set for the rest of the way because it had its starting point. If we look at this other strand, RNA polymerase laid down those RNA nucleotides here, but the daughter strand is building in this direction. So DNA polymerase building. Uh-oh, it ran out of room. There's no more nucleotides up here for DNA polymerase 3 to build for the daughter strand, and the DNA is unzipping in this direction. So this is where primase would come back and tell DNA, all right, now you got to start down here. So I'm going to lay some more RNA primers for you so that way you can continue building DNA nucleotides. So DNA polymerase 3 comes, builds, then same thing. As the DNA keeps unzipping, primase has to find another place to put RNA nucleotide primers so that way DNA polymerase 3 can build some more nucleotides. It's building them in fragments, in sections. See how this is one fragment starting with the RNA primers here. And then this is another fragment starting with those RNA primers here. Those are called Okazaki fragments. Okazaki fragments are created on this lagging strand. It's lagging because it's moving in the opposite direction that helicase is unzipping the DNA in. The daughter strand is building in the opposite direction, which because DNA polymerase 3 can only build in the 5' to 3' direction, this problem is solved by the creation of these Okazaki fragments. So, and the fact that RNA primase will tell DNA polymerase where to start and give it a starting point to create these fragments. Okay, so once DNA polymerase 3 lays down the DNA nucleotides on both the leading and lagging strand, that is when step 5, DNA polymerase 1 is going to do its job. It has two jobs. It's going to change the RNA nucleotides into DNA, meaning it needs to change uracil into thymine and ribose into deoxyribose. And while it's doing that, it's also proofreading to make sure that there's no mistakes in the DNA. After DNA polymerase does this to both strands, that is when the final step occurs, which is step 6. Ligase is going to seal the gaps between the Okazaki fragments of the lagging strand. So it makes sense because you're removing nucleotides, removing RNA nucleotides to replace them with DNA. So you're going to need to replace the gaps in the backbone from doing that. So that's when ligase comes into play, being the final step. Right, so Okazaki fragments were created on the lagging strand, meaning that there's no bond between these fragments because they were created discontinuously. It wasn't a continuous strand, it was broken up. So ligase is going to seal the gaps between the Okazaki fragments by creating phosphodiester bonds. So that is the last step, is the ligase sealing the gaps of the ligase. Ligase can also be used to not only replace the gaps in the backbone between Okazaki fragments, but ligase will also replace the gaps in the backbone from removing the RNA nucleotides. So it is used on both the lagging and leading strands. Now, the only problem is, obviously this lagging strand is a lot of work. It does involve more things, right? So primase needs to lay down these primers multiple times before that fourth step where DNA polymerase 3 can start putting down the nucleotides. Now we have the creation of these Okazaki fragments. And see how there's two fragments here, but there's going to be a space, a gap in between them. Why? Because they're separated fragments. They weren't built in one continuous strand like the leading strand. Their backbone is a continuous backbone. Here, there's a gap between these Okazaki fragments and these Okazaki fragments. So there's a gap in the backbone between the one nucleotide and the other nucleotide. That's when ligase comes. Ligase will come and fill in the gaps by placing that phosphodiester bond. So that way the Okazaki fragments can create a phosphodiester bond just like the rest of the backbone. And that is ligase. So that would be the fifth step.